Thank you for the generous introduction. Excuse me, I have to change my glasses so I can see my paper. And from now on, I no longer see the audience. But so long as the audience can still see me, that's okay. Thank you for bringing me here. Always a pleasure to be in this beautiful city. So thanks to the organizers, and thanks to the audience for being here so early in the morning. You're welcome to fall asleep at any time. I shall not see you because of the glasses I just changed. It is worse if I fall asleep while I read my paper because you will see me, but there is coffee, right? So in case of need, we can do that. So let me start with a topic we are all familiar with, as just mentioned, a topic which is everywhere. It has been everywhere for the last 30 years at least, for the design professions, the elephant in the room, the topic that everyone in our profession has something to say for or against. Computers. Computers are machines, so we tend to think that they work like all the other machines we know, but they don't. Computers are a new kind of machine, quite unlike any other machine we have ever seen. If we use computers to make stuff, to produce physical objects, computers make stuff following a technical logic that is the opposite of that of all the mechanical machine we knew during the modern industrial age. And let's go one step further. If you use computers to process information or to think, or something similar to that, computers seem to think following a logic that is the opposite of that of modern science, the science of Galileo and Newton, the science we all studied at school. Computers make things the way a good artisan workshop could, not the way any modern factory would. And computers think, or something similar to that, following the learning logic of a little child, not the scientific method of any modern engineer. And yet, in spite of their artisanal way of making and of their childish way of thinking, computers are effective. And they work so well that we already use them to solve many daily problems. Old problems, but also some new problems. Problems we could not solve in any other way. Which is why it is important for us to try and understand how computers make things and how they think. Because their logic is so different from the logic of all modern technologies and all modern sciences we have developed over time. Let me tackle these two problems separately. First, technology, ways of making, the way computers make things. Then science, ways of thinking, the way computers think or solve problems. The technical logic of the mechanical machines that have powered the Industrial Revolution is well known. Modern industry is based on mass production and economies of scale. Most tools of industrial mass production use casts, molds, dies, or other forms of mechanical matrices. This is a big press today, and this is an old one, the original one, the first one, a printing press, Gutenberg's press, used to print books at the end of the Middle Ages. But the logic of printing is the same. A mechanical matrix, a cast or a mold, a stamp or a die, costs money. And once it is made, we must use it as many times as possible to spread or amortize its cost over as many identical copies as possible. This is the logic of industrial standardization. The more identical copies we make, the cheaper each copy will be. This is the logic of the Industrial Revolution, a logic that architects famously rejected throughout the 19th century and often beyond. 1 century ago, more or less to the day, Le Corbusier, Gropius, Mies, and the Bauhaus were the first to come to terms with Fordism and Taylorism, the first to claim that architect should design for industrial mass production. And this became the foundational myth of modernism in architecture, the story we all studied at school, or at least people my age did. Let's make all buildings, or part of buildings, exactly the same. Let's standardize building so we can mass produce them using industrial assembly lines. We can maximize economies of scale, make buildings cheaper. That was Le Corbusier's big idea in the 20s. Let's abandon our elitist, artsy ambition. Let's learn from the engineers. Let's mass produce identical, standardized buildings, cookie-cutter buildings, in the same way as industrial factories mass produce automobiles or washing machines. This was the project of industrial modernity. Standard products, standard buildings for standard men. Now, we may like that idea or not, but regardless of any ideological implications and in pure technical terms, that logic was right 100 years ago, because mechanical mass production really worked that way. But that logic is wrong today, because digital fabrication does not work that way. Digital fabrication, subtractive or additive, does not use mechanical matrices, casts, or mold. Hence, every piece, when digitally made, is a one-off. As the reproduction process does not involve any mechanical matrix or stamp or mold, there is no need to reuse the same form more than once to amortize the cost of its matrix, since there is no matrix. No matrix, no copies. Hence, making more identical copies of the same item will not make any of them cheaper. Making all of them different will not make any of them more expensive. Standardization no longer saves money. Individual variations no longer cost extra money. Just like 30 years ago, we learned that using a digital laser printer, we could print 100 identical copies of the same page or 100 different pages at the same cost per page. Today we know that we can 3D print 100 identical copies of the same chair or 100 different chairs at the same cost per chair. You may make more identical reproduction if you like, or if you need. In this case, I presume that's impossible, but you might ask the person who made it, who is in this room. He can confirm that. But don't say that making more of the same will make any of them cheaper, because that is simply not true anymore. That was true in the mechanical age. That is no longer true in the digital age. Now, all this has, of course, a name. The digital mass production of different pieces is called digital mass customization, and a digitally mass-produced series of pieces that are all different from one another is called a non-standard series. Mass customization, digital craft, the mass production of individual granular variations at no extra cost. This is the general mode, the default mode, so to speak, the most universal technical paradigm of a digital age. And remarkably, since we are in a design school, it's good to remember that these ideas were invented in a handful of schools of architecture in Europe and in the US in the early 90s. Digital customization, mass customization, was our idea. It was an idea invented and nurtured and developed by the design professions. This is so rare and unusual in the history of our profession that it deserves notice. For the first time since the Middle Ages, architects and designers in this instance were not technological laggards or latecomers. This time around, we have been the technical innovators, the pioneers, the trendsetters of technical change. We have been among the first profession to interpret and intuit the spirit of the digital age. And to this day, designers and architects are the best specialists of all things digital. Designers and architects, not technologists, not sociologists or philosophers, not economists, not bankers, and certainly not politicians who, to this day, do not have a clue. They do not have the faintest idea of what is going on. This slide is for them. And so much the worse for them. Let them dig their grave with their own hands, hoping, as a footnote, that they will not dig ours at the same time. Because digital mass customization is now spreading like wildfire in all areas and all aspects of today's life, economy, and culture. Greg Lynn's embryologic house, or his famous teapot, may have been an experiment 20 years ago. But today, the Fab Labs are a social movement. And from production to commerce, the logic of digital mass customization is spreading to, for example, Zipcar, which is upending the automobile industry, Airbnb, which is upending the hospitality industry, Amazon's Mechanical Turk, which is upending the gig economy, and Bitcoin, for better or worse, it is upending banking and finance. Digital mass customization is likely as important today as the assembly line was in the 20th century or the steam engine was in the 19th century. But since this was, as I said, our idea, a design idea at the start, let us look at architecture proper, which is what we do, and ask ourselves, what is the visible sign, the visual evidence, the trace, if you like, of a new, fully digital mode of design and building? Are buildings designed and made using digital tools different from the others? If a building is designed and built using digital tools, will that show? Can we look at two buildings and say, this building was designed and built using digital tools and this one wasn't? If we ask this question to any of us, design students or professional designers, the answer will likely be that digital architecture or architecture of the digital age looks like this, this, or this. This is what we are mostly going to see. Smooth, curvy, streamlined lines and surfaces. And indeed, if we Google digital design and fabrication or any similar keyword like parametricism, computational design, etc., or if we look for any of these terms in Pinterest, Instagram, and this kind of stuff that you young people use, these are the kind of images we are likely to find. Whereas, if you have a look at what is happening these days in my school, or in a few other schools where new experiments in computational design are underway, you are likely to see stuff that looks like this, or this. You probably have seen that around here, right? And this. Hence, not at all smooth and clean and curvy, actually quite the opposite. All this stuff looks disjointed, disconnected, rough, angular, fragmented, aggregational. All that was digitally smooth now is digitally rough. All that was digitally continuous now is digitally discrete. This begs not one but two questions. First question, why should early computer-aided design, starting from the early 90s, generate smooth and curvy lines? what is the link between digital mass customization, or more in general, digital design and fabrication, or the style of a curvy line, smooth curves like this one? And second related question, if computers were so good at making smooth and clean and curvy lines 20 years ago, why is it that today, almost one generation later, most young, alert, smart designers using computers do not do curvy lines anymore, but they do rough and messy fragmentary volumes like these ones? Again, let me tackle these two questions separately. The reason why the first digital turn in architecture generated a style of smooth and curvy lines, which today many call parametricism, are well known. It is a complicated story, but let me recap it in a nutshell. This was mostly due to a story of boats, fish, and to Frank Gehry's noted fascination for both, but particularly for fish. We do not know very well how that came to pass, but at some point around 1990, Frank Gehry was commissioned to build a big fish, hovering over the Barcelona marina, to be inaugurated on the occasion of the Columbian exhibition of 1992. The technical problem for Gehry's Los Angeles office was how to notate, calculate, and fabricate the smooth and curvy surfaces of the body of a big fish. And this is when Gehry, or someone in Gehry's office, noticed that a fish moves in water the way a boat moves in water. Hence, the same technology used in shipyards to build the curves of the keel of a boat should be good for an architect trying to build the curves of the body of a fish. As the streamlining, literally streamlining means the curvy line of the stream, line of the stream, the streamline, the line of contact between a body moving in water and the stream of water around it. So this technology should be the same in both cases. A fish is streamlined because it moves in water. That's nature. A boat is streamlined because it has to move in water. That's the way we design it. In a sense, copying the fish. Shipbuilders had been developing streamlining technologies since the beginning of times. And the curving slats of timbers that allow the smooth movement of the keel of a boat in water by reducing drag and friction are called in English splines, a term that is recorded in English with that precise technical meaning since the 17th century. In the 20th century, aircraft makers and automobile makers had been developing similar streamlining technologies for similar aerodynamic purposes. At the beginning, all splines were still entirely made by hand, by artisan model makers. Then, between 1958 and 1966, two French car makers, Renault and Citroën, separately and in direct competition with one another, started to calculate splines using mathematical formulas. And to this day, mathematical splines are also known as Bézier's curves, from the name of a French engineer who first found a way to script splines using a mathematical function. Bézier's formulas were in turn the basis for the first spline modeling CAD/CAM software, adopted first by Renault and then by all major car makers and aircraft makers around the world as of the early 80s. And this is how, in the summer of 1991, when he had to build this big fish, Gehry did not find any suitable software among American shipbuilders. But he did find what he was looking for in Paris, in the offices of Dassault Aviation. And this is how a big fish in Barcelona was built using a software, CATIA. It was designed to build the wings of the Mirage fighter jets, using mathematics originally developed to streamline the hood of cheap Renault automobiles. The result was so successful that this peculiar kind of digitally streamlined curves, or digital splines, remains to this day the hallmark of Frank Gehry's architecture. After his Guggenheim Bilbao, designed and built soon after the Barcelona Fish, it was replicated by Gehry in many famous buildings around the world. This spliny style soon became very popular with many young digital designers who could not afford to buy heavy industrial-grade software like CATIA, and used instead cheaper and simpler programs for computer-aided design like Form Z, or Form Z, or Rhino, or even animation software like Maya to obtain similarly streamlined aerodynamic curves. In the mid-90s, Greg Lynn famously introduced the terms folds and blobs to define this new digital style. And today, following Patrick Schumacher, many prefer to call it parametricism. But if we consider the story of how all this came to pass, all these buildings should be more appropriately called fish. This is a fishy style, the style of digital fish making. All these lines or splines are literally and originally the curves whereby boats and fish alike move smoothly in water. So these are, in fact, all fish. Now, these fishy lines are evidently the best solution to build the wings of a plane, the hull of a boat, or the body of a fish, or even famously the sliding slope for an Olympic ski jump. Because if you have to slide over that slide, it's better that it is smooth. You couldn't slide on it if it has steps. So in that case, which is, by the way, the moment where Za really adopted streamlining, because in that specific case, she couldn't really do anything else. Then she liked the exercise, and she kept doing it, but that's another story. But unlike fish, most buildings don't swim. Unlike skiers, they don't jump. And unlike airplanes, most buildings don't fly. Hence, we may assume that most regular buildings, the kind of buildings we build and use in daily life, do not really need streamlining. There are exceptions, of course. Aerodynamic, streamlined forms were already used in the past for buildings related to transportation and meant to suggest or evoke an idea of speed, which is what streamlining is about. Saarinen, for example, famously built this between 1955 and 1962. And he did it without any computers at all. This is not a flying building. It's a building that suggests the idea of flying. That's an air terminal. Well, now actually it's a hotel, but it was meant to be an air terminal, and that's fine. But today, even after almost 30 years of digital streamlining, the case for a flying bakery, for example, or for aerodynamic social housing still seems far from compelling. This would seem to suggest that the rise of digital streamlining in the 90s, or the style of a digital spline, might have been, back then, when it happened, almost a quirk or a fluke, an ephemeral accident of history. At the end of the 20th century, digital spline modeling, or digital streamlining, was old science, carried over onto a new technology. The mathematics needed to make a spline was entirely scripted between 1958 and 1966. And Bézier didn't use any computers at all to do it. Splines were not new in the 90s. They are not now, even if we are getting better and better in making them bigger and bigger. But let's move now to the second part of my query. If digital continuity, the style of the spline, was little more than a trivial accident of technical history, what about today's second digital style, the style of digital discretism? Where does it come from? Why is it replacing digital spline modeling? And how does it relate to computers if splines essentially, mostly didn't and don't? I think that discretism does relate and essentially pertain to computation for one simple reason. It speaks the same language. Let me explain. Computers today are not much different from those of 30 years ago. But they are faster and more powerful. And due to their sheer force, to their brutal, unprecedented, overwhelming power, they are now pushing us to use them in new ways. Ways that are based on the way computers think, not on the way we think. There are many new terms in use today to describe today's advanced computing and its novelty. Brute force computation, big data, dataism with a T, artificial neural networks, machine learning, deep learning, generative evolutionary algorithms, or even more generally, artificial intelligence. A term, by the way, which is not new at all, as it was invented in the late 50s, when computers looked like this, and abandoned in the 80s, when computers looked like this, and which is now being revived. But to be brief, let me show the novelty of today's new brute force computation with a couple of examples taken from the daily practice of our profession. Bézier's splines were continuous lines mathematically notated using analytic geometry and calculus. The equation of a spline is, of course, a bit more complicated than this. This is about all the calculus I know. But this is the principle. This is the notation of a very simple continuous line, a parabola in modern mathematics. Analytic geometry and calculus were invented in the 17th century or early 18th century by Descartes, Newton, and Leibniz. But we still use calculus, and we still study it at school, because calculus was a very smart invention, a very smart way to notate as many points as possible in the simplest, shortest possible way. Let me put it this way. How many points belong to this line? Well, as we know from school, this line contains an infinite number of points. But using calculus, we can notate all of them using just 2 letters and 3 numbers. This simple, short formula contains all the points we may ever need to draw or produce that line at all possible scales. Calculus is scaleless. That notation has no scale. Big parabola, small parabola, still written that way. And yet, this is not computers. This is not the way computers do it. To notate this simple curve, a computer would typically write down a long list. A list containing the coordinates of each single point belonging to that line, as many as needed, if necessary, a huge number of them. Literally, a never-ending list, as you can always add more points when needed. No human could work that way, because that would take forever. Writing a never-ending list is literally a never-ending task. But computers can work that way because they are fast. So fast that they can do in 1 minute more calculation than we would in months. Computers are so fast that they do not even need to be smart. Computers don't need to learn calculus, which is why they don't go to school, as they will never need to use formulas or functions. These are the 2 logics, the formula, calculus is for us. The function is for us. The list is for them. For electronic computers, a list containing the coordinates of 4 million trillion gazillion points is just fine. Now, in a design job, at some point in the course of production, these mathematical points must become physical pixels or voxels. Starting some 10 years ago, some designers concluded that as computers really work that way, by listing and itemizing 4 gazillion voxels one by one, that enumerative logic, the list, the log, the inner logic of what computers do, might as well be shown and displayed in their finished computational work. That was the start of the style of voxelization, or discretism, or discrete design computing, the style of excessive resolution. But excessive for whom? Evidently not for computers who did it, but excessive for us, because we, humans, we could not do it. What we see here is the outward and visible logic, no, the outward and visible sign of an inward invisible logic at play, which is no longer the logic of our mind. Not surprisingly, some claim that this looks strange. It does, because this is not the way we think. This is no longer a word we can comprehend within our minds. Let me give you another example taken from recent developments in digital design. When we design something, it helps to know that the building we have designed will stand up after it is built under some predictable loads and in certain normal condition of use. Structural engineers typically use formulas like these, a bit more complicated, to predict the structural resistance of most structures we build. But could we use this kind of science to calculate this kind of structures? No, we can't, because the structure is too complex, made of too many different parts, and to calculate each very small segment or particle of it in the traditional analytic way would take forever. Which is why structures like this are not really calculated anymore. Instead, they are tested in simulation, using now standard software for computational finite element analysis. And in short, that's the way it works. The designers start with the model of a more or less random structure, then apply some simulated loads onto it. When they increase the loads, they will see that at some point, some parts of the structure will start to give way, which the software typically flags by showing some error message. And the weakest part of the structure, those that would snap or break, start flashing red or blinking on the screen. When that happens, the designer will tweak the structure a little, often equally randomly. Then reapply the same loads until the structure breaks again, likely somewhere else. And so on and so forth, until the designer, after many trials and many errors, will find again more or less randomly a structure that doesn't break. And that will be the good one we want to build. Now, this is not unlike what a traditional artisan making chairs by hand in his workshop would have done. You make a chair, if it breaks, you make another, and then another, until you make one that doesn't break. Where today, making and breaking in simulation on a screen costs nothing and is much faster. Today, using computational simulation, you can make and break on the screen in 1 hour more chairs than a traditional craftsman would have made and broken in a lifetime, often learning something in the process. Therefore, trial and error, which is a very wasteful and ineffective, even dangerous strategy, when carried out in real life, is a perfectly reasonable and viable strategy when carried out in simulations. In fact, using electronic simulations, we do not even have to spend time to keep trying ourselves. If we get bored, we can just tell the machine, the computer, to keep trying automatically until the program reaches a solution that will match certain parameters we have set. And we call that optimization. Cheap, user-friendly programs like this one, Galapagos, a Grasshopper plugin, can do that in no time. If one can try 1 billion, 1 trillion, 1 gazillion randomly different solutions per minute, it doesn't take any degree of intelligence, either natural or artificial, to find at some point a good fix. A fix that will be good enough to solve the problem at hand. Just keep trying and keep trying. At some point, you find the good solution. If we do it, it will take 1,000 million years, so we don't do it. The computer does it, takes 3 minutes. So computers can do it, we can't. So again, what we see here are two different strategies at play. Ours, which is based on scientific formulas, which in turn derive from centuries of experiment, intuition, abstraction, generalization, theories, and intelligent understanding. That's us. And then there is the computer's logic, which is based on big data and pure, massive, brutal trial and error. Some call it a new kind of science. And it's true. It is a new kind of science, except it is not our science anymore. And it shows. Example, if we look at most structures designed by humans, we generally can tell why and how they stand up. The formulas of structural engineering are causal formulas. They establish some relationship of cause to effect between loads, forms, and stresses in a structure. Engineers use these formulas to calculate the resistance of a structure after it has been designed. But they use the same formulas to drive and inspire their first intuitive design of it. This is because causal laws make sense somehow. By the causality they express, they interpret and provide some understanding of the physical phenomena they describe. Indeed, this rational meaningfulness and the structural theories underpinning it are visible in all the masterpieces of modern structural engineering, from Eiffel's towers to Nervi's vaults. If we look at these modern structures, we understand the basic structural principles the designer had in mind when they first sketched them. If we look at this structure, we don't have the faintest idea of how and why it stands up. Why does this one structure stand up and the 1,000 we just tried and discarded in computational simulation didn't? Nobody knows it, least of all its designers. And yet, it does stand up. Using digital simulation, we know in advance it will, which is why we can build it. More examples could be added, taken from design, technology, and even from daily life, where plenty of evidence already suggests that today's computational brutalism, or brute force computing, is upending most of our traditional thinking. And it is already pushing us to think, plan, design, and act in ways that until recently we would have thought impossible or absurd or even magic, beyond human understanding. To revert to the two cases I just mentioned, voxelated discretism and structural design by trial and error. Think of what we did using computers that no human could ever have done. Nobody can design a building made of 4 gazillion different particles because no one can notate, calculate, and fabricate 4 gazillion different parts of a building one by one. Likewise, Nobody can test the structure of a building by running 4 gazillion different structural trials in a row, because that would take forever. Yet, using brute force computing, this is exactly what we are doing today, whether we realize that or not. Because this is what computers do. This is what computers are best at doing. And by the way, some may find that disturbing or worrying or worse, and yet this is just the beginning. Because the best way to combine the technologies of digital mass customization and the scientific logic of brute force computing today implies the use of robotic manufacturing, as only robotic tools can be flexible and versatile enough to assemble an infinite number of different parts, or identical parts, which we can now mass produce in an infinite number of different ways, which you can now notate and calculate each and all one by one. And if on top of that, we try to imagine how artificial intelligence may soon leverage today's technology for robotic assembly, the most likely next step is easy to figure out. This should move. Does it move? Yes. I didn't do it, but the person who did it is in this room. Well, why not? At least a self-building building is going to be less dangerous than a self-driving car. To conclude, all suggest that design and building will soon be and look very different from almost all we have seen and known to this day. So much different that this time around, looking at our recent past may not provide any hint to help us figure out any way of dealing with our imminent future. In fact, as I've been arguing for some time, looking at our distant, pre-industrial, artisanal past may well be more inspirational for us today than looking at our recent industrial or post-industrial history. If you ask me personally, I may like this or this very much. I do like this one a bit less. But our computational future is not going to look like any of that at all. And this is my last word for today. Thank you.
Thank you very much. We have time for questions. Are there questions? And do we have a mic for questions? The first question is always difficult. Who will do it? Well, we can't let Mario go without questions. There it is.
I'm fine. If there are no questions, fine.
I have a question regarding if the imminent future of architecture is going to change dramatically in unforeseen ways, but humans don't adapt to change that quickly. My question is, how long could this transition last? Because if we look at what humans prefer, they prefer what they know, what is familiar to them. This computer-generated designs and architecture is something very strange, and I don't know anybody who would rather prefer to live in a house that looks like a fragmentation of time and space, aside to a very nice, modern Nordic-style house. So if it's imminent, then is it really that imminent, or is it a long process that we will, well, perhaps we will never see, but our children's children will see?
Well, you're a bit younger than me. So my guess is that you will see more of that than me. But it's, you know, this is a never-ending issue of the adaptation, as you rightly said, between technical change and human traditions. We always tend to cherish what we already know. But this question you have been asking me, if we had been at the Bauhaus in 1920, someone could have been asking any of those teachers down there, they could have asked, why do you want people to live in buildings that look like machines? Whereas since the beginning of times, we have been living in buildings that were handmade. It took a long time for architects to come to terms with the industrial mechanical way of making, and it took equally a very long time for humans to get used to the idea that they could live in a mass-produced industrial-looking building. But then, when they started to like that idea, they stuck to it. And now they like it so much that you're telling me that you would like to live in a building where your grandfather would not have liked to live, because your grandfather or grand-grandfather, seeing a modern, stylish, Nordic, modernist building, would have said, this doesn't look like a building. We always lived in handmade buildings, because this is the way things have been since the beginning of time. How long did it take for humans and architects to come to terms, to get used to the industrial revolution? And how long it took for architects to develop a design culture that could capitalize on that and make modernity looks appealing? We must conclude that they did it a bit late, but when they finally started doing it, they did it so well, but so well that now, 100 years later, we still like what they did. Witness the question you just asked. How long will it take for your generation to do the same thing that your grandparents did? That I cannot tell. But to this day, there are already, if you ask, marketing people or people in finance, there are people that are going to tell you that the real estate value of some signature building by spline modelers and blob makers of the 90s is very high. So there is a market for that. So there are already people who are willing to spend more money to live in a spliney fish by Frank Gehry and Zaha did than, so the transition has already started. How long will it take before it becomes mainstream? I cannot tell you. But one thing I can tell you, it will become mainstream. Because computers today, whether we like it or not, are going to do to our way of life what the Industrial Revolution did to Europe 200 years ago.
Where was the question? Oh, it's okay.
Mario, thank you very much for your lecture and your polemic challenge. And I like to understand it maybe a little bit better, or I have a wrong reading of it. But it almost feels that we are at the forefront of a new kind of technology, which is without an ideology, in the sense that the modern movement, also like Walter Benjamin, for instance, who said that the new critique should be like the advertisement, or another way, can we hijack or mobilize these technologies for a new ideology, or maybe for a new imagination, which is maybe another one than the one from neoliberalism, who is now financing it. So how is that relation between ideology and technology? But then I like to ask the question from the point that you in a way raised, that it brings an openness, a non-defined moment yet. What I also will tell in my short talk is that Jean-Luc Godard jumped on 3D technologies precisely as he says, there are no rules yet. I'm not yet defined in a straight jacket, the market has not yet controlled it. So that freedom allows me to maybe even arrive at another idea of civilization. So would you plea for that maybe we as architects, as politicians who are indeed blank, have to bring the ideas back into what these technologies provide, or investigate that? So what's the relation between ideology and technology?
That's a $1 billion question. But computers are versatile, and they take orders from whoever owns them. Regardless of the fact that it is true, in the 90s, the digital turn was mostly hijacked, as you said, by neoliberal people. I don't think there is nothing inherently neoliberal in the technical logic of computation. Again, the same parallel. The industrial moving assembly line was invented by Henry Ford, who had strong ideologic views of society. But in the course of the 20th century, every ideology and every society around the world has adopted exactly the same technical logic. Stalin was crazy about Fordism, and he wrote in favor of it. Fordism, Taylorism, the industrial assembly line, was adopted by liberal society, by anti-liberal society. It was adopted by social democratic societies. It was adopted by Soviet societies. They all adopted them because it made technical sense. And so there is no way you can claim that the industrial moving assembly line has an ideological preference. Likewise, I don't think that digital mass customization or computers as a tool have an inherent ideological bias. If we want to tackle the ideological question in these terms, we should ask ourselves, what would a great Marxist, for example, a certain Karl Marx, for example, how would he have tackled the question? The typical Marxist answer to this question would be, don't ask what computers do. Ask who owns them. The social relationship between the ownership of tools of production and the productive forces, Karl Marx Capital, Book 1, still applies. The added value of the use of computers will play out in socially different way according to who owns them and how are the profits distributed. But this does not depend on computers. This depends on the ideological choice we make when we go and vote. So don't ask computers what they can do for society. Ask societies what they want to do with computers. As architects, we have evidently our own ideological choices. And you know, strange as it may seem, some architects around the world are neoliberal. I know some, but not many. So it can happen. And it is true, there were many in the 90s. Now there are fewer of them. But they will use computers more or less in the same way as we all will use them. And then when we vote, they will not vote the way we vote. But the machines they use are likely to be the same machine we use. It is true that today we must, that's my personal opinion, we must ask the question of the economic logic of computers with regard to labor, economics, cost, and particularly the environment. But not everyone shares this ideology, and others will not. In my personal opinion, what we need today in this particular time and place is, that's a joke we had with friends, we do not need today object-oriented ontology. We need socially oriented computing. But that's just me.
Yep. A short question and then I stop. Also with the technologies of the modern movement, it also arrived at another aesthetics and another spatial experience. So, for instance, the spaces became continuous, the relation inside out changed, the idea of ground, the way of alienation, top and bottom, etc., etc. So, within the aesthetics itself, it provided another way of living, another way of the aesthetic experience, etc., etc. Now, this recent technology, we don't know yet what it produces, but it produces another aesthetic experience, another sense of how difference relates, for instance, of what you also hint to, which is very interesting, from the streamlining a kind of symbolism or metaphor still referring to nature and what we know, while the new computational technologies establishes many multitude relations, etc., beginning and ending. So that is another kind of aesthetics, with another political effect or an idea, an ideology embedded within its aesthetics. Or would you disagree?
No, I agree. That's a statement. I mean, but yes, okay, fine. Coffee, yes.
Because we have plenary session at the end, so we have time to ask a question there.
Thank you, Mario, for a beautiful lecture. I had one observation which will lead to a question. You know that Diderot famously asked himself, what is mechanical in the way our mind functions since we invent machines? And you yourself suggested that there is something childish in the computer, and actually, historically, humans have been reasoning with lists for centuries before turning to more elaborate and synthetic method. And last element, you know, calculus, when it emerged, was very, very mysterious, almost unhuman for, I worked a lot on its emergence in the 18th century, and actually it was by no means a smooth, intuitive move. So could we rather, have a slightly different end to your story, that instead of the radical otherness of, the computer, see a kind of new convergence through the way we tend to reprogram ourselves after having invented machines. In other words, the computer may be different, but we invented it, and aren't we, because if we want to inhabit those strange constructions, we probably need to develop some intuition that makes them human. So in some ways, instead of this radical otherness, could it end by, in some ways, or becoming probably different, so that the computer makes sense?
Yes, if I only could answer this question. Time will tell. My take on the matter is that when artificial intelligence tried to imitate the way we think, it didn't work. It was famously a flop and a failure. Artificial intelligence seems to work today, and it does work, to the extent that we are no longer trying to imitate the inductive process of formalization and abstraction of our mind. We let computers unleash the brute force of massive computational trial and error. And so the reason why computers can do, or artificial intelligence can do today, things that 30 years ago they couldn't do, is that 30 years ago they tried to program the machine emulating the inductive capability of the human mind. And now, to some extent, we have abandoned this trial and we let computers win the game, not by being smart, but by being brutal, brute force computing. So, but I'm not a specialist of computer science, so this is what I was told, and I take it as a matter. If that contention is true, and then we should assume that at present, the logic of our mind and the logic of computation are different, and they are working in different ways. My personal take is that we should we should each keep to what we do best. So just as trying to use computers to imitate the way we think didn't work out very well, likewise, we should not try to rewire our mind to try to imitate the way computers think. I think we should keep our way of thinking for us, which is quite good for some things we can do and computers cannot do. And we should let computers think in their own way to solve problems that we could not solve in our own way. À chacun son métier. Let's keep for us what we can do well with our traditional way of thinking. Let's devolve to computers what they can do better than we could using their own inhuman or post-human way of thinking. But let's not try to imitate them, just as it turned out that it wasn't a good idea to program computers to imitate us. It's us and them. We can work together, but separately. That's my take. But I may be proven wrong.
Last point of disagreement on that is that you have a vision of the human mind which is so rational, but actually a large swath of what we do in our mind is akin to a kind of giant computing and unconscious machine.
Yes.
So you could say that actually part of us functions like a computer. And to finish, I could also counter by saying, we don't function like an automobile. Walking is very different, but we have internalized a lot of ways the automobile function. Doesn't mean we've become automobiles, but we're able to. Anyway, to be continued.
To be continued.
Take the last question, Roland, and then we go.
Mario, thank you for the wonderful presentation. Maybe first an observation and then a question. And the observation is something around the difference between discrete operation and discrete aesthetics. And I think these are fundamentally different things. So computation, of course, is discrete. But the way that is reified is actually a strategic decision. So, which I guess leads into the question. You mentioned briefly political things, but maybe the question is really around the politics of architecture or the strategies of architecture. And I wonder whether the smooth and continuous of Greg Lynn's generation was really a reaction against deconstruction.
It was, yeah,
okay.
Evident.
And then I wonder whether the work of our friends at the Bartlett, is this a political reaction against the smooth and the striated and the supple of Greg Lynn? Or because you sort of position it as though the spline was a mistake of history, a coincidence. But now we're moving towards what is the real and the truthful expression of the digital. But I wonder whether it's just a generation of architects who must, by the very nature of being radical, react against their predecessors and propose the opposite.
That's a very good point. Every generation of architects have a tendency to do the opposite of what the previous generation was doing. So it is absolutely true that Greg himself, in his writings of the mid-90s, was advocating his rejection of the angularity of deconstructivism while he was working in the office of Peter Eisenman. So this is a complicated father to son story. So it is interesting if you look at what both of them were doing in the late 90s. When Greg finally built his church in Queens, Presbyterian, I forgot which denomination it is, it looked like a Peter Eisenman building. But when Peter, at the same time, started to design the Compostela landscape, he was designing it as if he had been Greg. So there is always some of that. And it is true that after an inflation of spline continuity, and also due to the influence of the writings and of the personality of Patrick Schumacher, particularly in London. He's our neighbor, we see him often, he's often invited, and so. And given also his stark ideological and political choices, it is evident that a new generation of designers who often started designing with him or with Zaya wanted to do something which is just the opposite. So yes, that, permanent cycle of upheavals is inevitable in the history of design. But I still also think that the inflation, the style of the spline or digital streamlining in the 90s, it was not an error. it has changed architectural history. It is in the history books. It happened. It was real, so it must have been rational. There are many reasons to explain how it happened, but it did happen. When, you know, architectural history books are written on the 20th century, the 90s will be the 10 years of spline modeling. So it was important. If it happened, it had many reasons to happen. It has marked the history of design and the history of civilization, in a sense. When the first splines were built in the 90s, there were the visual representation of the fact that computers at the time represented a new universe of technical and even social possibilities. It was seeing the Guggenheim Bilbao inaugurated was, for those who were young at the time, the same as for my generation, seeing the inauguration of the Centre Pompidou in Paris, something that came from another planet. First time you see it, you didn't believe it was possible. When you went to see it, you touched it, was possible. It meant that something big was happening. So, and yet, it is a fact that from a pure technical point, all the mathematics needed to make spline had been around for 30 years. And all the craft needed to make splines had been around for centuries. So it was really the carrying over of a pre-existing technology onto a new technical platform that made it faster, cheaper, better, and bigger, but conceptually not new. Whereas discretism, what has been happening for 10 or 15 days, is something that could not have happened before, because you couldn't even conceptualize the notation, calculation and fabrication of 4 million trillion gazillion little particles. This is really something which represents the age of computation in the way that the spline did, but mistakenly so. Time will tell.
Thank you very much.
Thank you.